In this video, I want to go over some warnings about using Pearson correlation. And it's really great when you use it right, but when you use it incorrectly, some bad things can happen. So you should remember that you should only use it for scale variables and only for linear relationships. It doesn't work well when you use it for categorical. I don't know even how you can do it for that. Or if you give your categories kind of numbers, but they really shouldn't have numbers, you shouldn't do a Pearson correlation. Also, don't do it on curved relationships. Pearson's correlation does not work well for curved correlations. There's some other things that we haven't gone over, and one of those things is extrapolation, and that is when you interpret results outside of where you have data. So we extrapolate. So here is a scatter plot of weight versus salary for men. You can see over here we have salary, and down here we have weight. And we have data in this region. Okay, and it shows that as your weight increases, so does your salary. So if you think of this in terms of beauty norms as well as beauty norms, right? For the most part, men don't want to be too skinny or too unmuscular. And if they follow these beauty norms, maybe people respect them more and think that they're better workers and they get a higher salary. Even if that's not really true, maybe, men of all weights are equally productive. So we have data from here to here, and this relationship is actually pretty true. I found it to be until you get to a certain weight level. This isn't real data, but this is kind of made up data, but it's kind of based on real data. So until you get to a certain level, this is actually true. So you get pretty high to even a little bit overweight, this is true. That as your weight increases, so does the salary for men. Not the same for women, it's totally the opposite for women. But if we extrapolate here, this in blue, we would say that, and this is on extreme overweight situations. We are also saying that even if you're really obese, as your weight increases, your salary will also increase. And that might not be true, especially if we're just basing it on weight levels for the underweight to, the normal weight or a little bit overweight, not the really obese. So on this side is the actual relationship if you go to the really overweight. Now, it might not be as strong of a association or correlation here. Might not follow the line, the dots might not follow the line as well as they do here, but it's the basic trend of data is that as salary increases, so does your weight, and as your weight increases, so does your salary until you get to the certain point where it's too much overweight. And then the men aren't following the beauty norms. So what happens is when you get to the really overweight levels here, as your weight increases, your salary tends to decrease. Because now you're not following the beauty norms, now you're actually going against the beauty norms, you're too overweight. And so people think you're lazy and unproductive, which is probably not true, but people judge based on what people look like, and that can affect even your salary. So when we get up here, the actual relationship is different. So you don't want to extrapolate past where you have data, because the story beyond where you have data can be totally different, like it was in this example. So in this example, in the first slide, we just had data up to normal weight levels or slightly overweight. And if you go too far, and extrapolate too far and try to make inferences that are past or you had data, you'd run into things like this where you think even the very obese have salary increases, and you say that, but in reality that's not what is really happening. You really need to collect data where you are trying to make inferences. Now I want to talk about outliers. So an outlier is a person that's really not going with the trend of the other people. So here's two examples of outliers. The dots are really far away from the rest of the data. Now, sometimes outliers aren't a big deal, but sometimes they are. So this example, they actually are a big deal. It is messing with our line of best fit. So you can see the line of best fit kind of went up in the slope. So instead of being, it should have been here, around there. But now you can see it's moved up a little bit like this. So what happens is now these dots that are down here are further away than they should be from the line of best fit that it made. They would be closer to the purple line. And so if we did a correlation on the purple line and forgot the outliers, the correlation would be stronger than if we kept the outliers in and did a line of best fit of where the blue line is. Now sometimes outliers, depending on where they are, don't really affect the line of best fit at all. It just depends. So typically when they're kind of far away from the other ones, like up here in this area or like down here, even though we don't have any, sometimes they tend to affect the data a little bit more than if they were around this area. You don't really need to know too much about this for this class, but I just want to give you a little heads up that outliers do affect your line of best fit, and if they do that, they can affect the correlation, the strength of the correlation.